Photonic integrated circuits, or in short, PICs, are very similar to the electronic integrated circuits that you would have in your phones and computers. But besides the electronic part, they would have the optical part, so optical elements which are used for creation and manipulation of light on a microscale. PICs are used in many different industries, from aerospace and sensing to biomedical and telecom. In fact, if you're having iPhone X or any other newer version of iPhone, you're probably using PIC technology for unlocking your phone without knowing it. In case of iPhone X or any newer version of the phone, the PIC, which is inside of your phone, is shooting about 30,000 laser dots to your face. So these lasers are very low power and they are harmless, so there's nothing to worry about. But they're over there to make sure that your phone is not seeing just a photo of your face, but it can see the complete 3D image with all of the contours. So PICs are powerful and important, but since they're relatively young technology and they're extremely small technology, they're coming with their own set of drawbacks. As they are so small, interfacing them into any bigger system, electrically and especially optically, becomes very difficult and therefore very expensive. That is where PIXAPP Photonics Packaging Pilot Line is coming into place. It's an EU initiative aimed at helping small and medium-sized companies which are having great PIC-based technologies, but would generally struggle into making them into a complete device. PIXAPP is basically a partnership of more than 20 different research institutes and companies, which can complement the client company's technology into making a complete device, which then could be sold on the market.
You probably know how cars are made on assembly lines. Each robot does a small part of a very specialized work, and at the end of the assembly line, you get a complete car every few minutes. And PIXAPP works just like that. But instead of expensive robots in a single place, they are distributed around Europe and operated by different companies. The PIC then has to go to those different places for packaging, and at the end of this distributed assembly, we have hundreds or thousands of complete devices. The advantage of such distributed system is that packaging can easily be adapted to different devices which require unique assembly steps.
Here I would like to show you how that is done on an example of a datacom demonstrator. Within PIXAPP, 4 different demonstrators are being built to showcase usefulness of different building blocks and of PIXAPP as a whole. Datacom module is a transceiver basically, and transceiver is a device which is converting electrical signal to the optical and then vice versa. It's one of the fundamental nodes in the modern telecommunication systems. Within PIXAPP, it would all start with a discussion with the PIXAPP Gateway Office, which would discuss the client company's needs and try to match them with the most suitable packaging partner. In case of a datacom demonstrator, it was a bit different, and it was basically the agreement on technical specifications among the different packaging partners. The packaging of a datacom demonstrator was done in 4 different assembly strands. The first strand of the assembly starts with the central element, a PIC, which is designed and fabricated in silicon platform at IMEC in Belgium. Together with 2 EICs, they are all shipped to Argotec in Czech Republic, where the EICs are flip chip on top of the PIC. At the same time, the second strand of the assembly is taking place. A micro-optical bench containing a laser is designed at Tyndall Research Institute in Ireland, and necessary components are sourced to Cordon Electronics in Italy, where the MOBs are assembled and tested. The complete MOB is then again shipped to Argotec in Czech Republic for putting down on PIC. The third strand of the assembly is starting at the VTT in Finland and at Argotec in Czech Republic, where with joint effort they designed high-speed RF lines on PCB and LTCC interposer, enabling minimal footprint and very high-speed electrical data feed to the PIC. The interposer is then manufactured in Finland and is shipped to Argotec, where, together with the fabricated PCB and the dedicated connectors, it is assembled and put in the appropriate housing. The final strand deals with the optical interconnects. They are designed collaboratively between Cultural Institute of Technology, or in short KIT in Germany, and IMEC. The on-PIC pluggable design is then translated into microlenses which are deposited on PICs at IMEC, and the 3D printed lenses which are deposited on the optical fiber array connectors at KIT. As you can see, all the 4 strands are joining together at Argotec in Czech Republic, where the MOB as the last on-PIC element is put down on the PIC, and then it's interfaced to the LTCC and then to the PCB. The top plate containing the fiber array alignment element is the last thing to go over the PIC, and it's enabling optical pluggable connection directly to the PIC. I hope you enjoyed this small presentation and thank you for watching.